All right, so this video and maybe next video, this is where things start to get a little hairy. Just like the book I'm reading, which has these mechanical droids that are shaped like spiders, and for some reason the spiders have hair on their legs, and it's like if you have a robot, why would you add hair to the spidery legs? It just kind of gross, right? But anyway, we're going to be approximating area, which again I tricked you into doing in the last one, but now we're going to do it more straightforwardly. Okay. So remember our goal here, right? Our goal is, we have some curve and we're looking for the area underneath the curve. And we're going to do that by approximating that area with any kind of shape. It doesn't have to be rectangles. I just like rectangles because they're easy. All right. Area of a rectangle, length times width. I got it. No problem. You could use trapezoids. That's another very common method. You could use, I'm out of shapes. I'm out of shapes. Shapes are not my strong suit. You can use other shapes, all right? And you can decide where to draw the rectangles from and stuff like that. Different kinds of rectangles. All right, but you could use other stuff, but we're going to use rectangles. And it doesn't even matter that they're all the same size. It doesn't matter that they're all the same shape. But things are going to be easier if they are the same size and they are the same shape. It's just going to make the sigma notation and stuff like that a little easier. So we'll use the same size, same shape, but it actually turns out not to really matter that much. We're going to start with a definition of what it means to partition an interval. The short answer for this definition is if I have some interval, a partition is just dividing it into, I shouldn't use that. A partition is just dividing it into intervals. They don't have to be the same size, right? I divided this into like 10 intervals just now. That's all a partition is. We got this first interval, we got the second interval, and so on. That's what a partition is. The mathematical definition, a little bit more squirrely, but here we go. A set of points, and we can call that set capital P, and it's written with set notation, and it's a set of all the xi. Remember your set notation from like a pre-calculus class or something. The squiggly brackets means set, a set of all the xi. And let's say here that I starts from 0, and it counts all the way up to some number n. So there are n plus 1 points in this set, okay? And this, let's say this set of points divides an interval from A to B. Let's say it's a closed interval, okay? And it divides that interval into subintervals, just like we have in the picture, right? In this picture, A would be x naught, and then the first mark would be x1, and then x2, x3, x4, x5, x6, x7, x8, x9, x10. So here n would be 10, there'd be 11 of them. And we just divide them into a bunch of subintervals. So the subintervals are like, from like x sub 0 to x sub 1, and then x sub 1 to x sub 2, etc. You get the idea. That's called a partition. And these are going to be useful. Well, that's not how you spell that word. And this partition is called regular. The intervals are the same width. Regular partitions are going to make our life with area a lot easier. Again, they don't have to be the same width. They don't have to be the same size. That's redundant. They don't have to be the same shape, but things are going to be easier if we do have them that way. All right. So that's a partition. All it is you take one interval, you cut it into pieces. You have a pizza party. You take a pizza, you cut it into pieces. They don't have to be the same size. My piece can be a lot bigger than your piece. That's all a partition is, just cutting something up. The pizza cutter. I should have brought my prop, my pizza cutter. I just made a pizza the other day. I make a lot of pizzas. Oh, they're good. I had leftover pizza for lunch today. It was a tofu, tapatio, tomato sauce, mozzarella cheese, pizza with some basil and Parmesan cheese on top. No, really good. The tofu is whatever. Let's get on with it. All right, so let's do a problem. This is, oh, I didn't give it a number. Let's call it example 3.5 because it's between example 3 and 4. Okay, so let's see. Consider the approximation. We're approximating the area under the curve here. And I'm just going to draw a little picture. And let's say we're looking at the function x squared plus 1. And we're approximating the area between 0 and 1 by splitting it up into 4 different pieces. All right, and we're going to use left endpoint approximation. We're approximating the area like so. And pretend that all of these rectangles are the same width. So we're approximating the area under the curve of the function y equals x squared plus 1 between 0 and 1. We're approximating this with 4 rectangles. Okay. Now what I want you to do, we'll do it together, don't worry, is find the approximate answer, the approximation. Find the approximation and write that approximation in function and sigma notation. There we go. I'm finally writing sigma out. The side note, you know, if you ever see guys calling themselves sigma males or something like that, or women calling themselves sigma females, now you know what they're talking about. They're talking about calculus. They're talking about adding things up. That's a little bit of modern slang, free of charge for you guys. Okay, so find this approximation. Well, all we have to do is add up 4 different rectangles. Well, what's the length of the rectangles? They're all the same size. Well, the first rectangle is 1/4 in the width. The second rectangle, wait, they all have the same width, right? They all have a width of 1/4. What's their height? So again, this area is going to be the width times the height, plus the width times the height, plus the width times the height, plus the width times the height. We got 4 rectangles. Well, now we just need to find the heights. This distance right here is the height of that first rectangle. How tall is that? Well, it's just a function value, right? The height here is a function value at that point. It's just f of 0. 0 squared plus 1. The height is 1. Right? F of 0 is 0 squared plus 1. We're gonna need that later, right? 1 is f of 0. The 1/4, that's the width. And now we can continue on with this process with the next one. Let's have the next one be blue. What is this blue distance? Well, it's just the height of the function at 0.25. We're going to say, all right, what's the function value at 0.25? Square it and add 1. It's going to be 0.0625 plus 1, I think. Square 1/4 and add 1. Let's make sure I do it right. 0.25 squared plus 1, 1.0625. Great. And just do that again. You're going to get 1.25. And then do it at the last one, which is at 3/4, which is going to be, I don't know, 1.5625. So this area, this approximation, is just whatever all this is, 1/4 times each of these. So I can just write the 1/4 out in front and use parentheses. The first one, 1.0625 plus the second one, Wait, the first one was just 1. Plus the second one, 1.0625, plus the third one is 1.25, plus the fourth one, 1.5625. And there are 4 rectangles. We've added 4 things up together. We get 1.21875. That's the approximation of this area. Turns out the actual area would be, the actual area is supposed to be, I think it's at 1 1/3. So 1.3. So we're slightly under the actual. We estimated 1.2. It's actually 1.3 repeating. And it makes sense that we're underestimating the area, right? We're missing out on this section. We're missing out on this section, right? These rectangles are missing out a little bit. Okay, so we found the approximate area. Now part 2. Right, with function and sigma notation. We're really close, right? We said it's just the width times the function value at 0. All right, so we just need to add it all up. So let's use this and work with this on the next page. This is the area. Let's write it in function notation. Again, it's always just the width times the function value at 0. This was the function value at 1/4. This was the function value at 1/2. And then the function value at 3/4. So how do we do that? Well, it's just going to be the sum from I goes from 1 up to 4. There are 4 pieces. 1, 2, 3, 4. And every piece has 1/4 times the function value at 0, 1/4, 1/2, or 3/4. And this is where things get a little squirrely. I said I promised some squirrels, and this is where the squirreliness starts happening. All right. How do we put this stuff inside? And that's not something we've really introduced yet. So let's look at the relationship between these. 0, 0.25, 0.5, 0.75. In the meantime, let's just write this as an x sub I. Okay. So if the first one is 0, actually it's a little easier if you use I minus 1, but it doesn't really matter. You can do either one. Right, x sub 0 then, when I equals 1, this is x sub 0, needs to be 0. I'm pointing with my finger. You can't see that. The first one, when I is 1, you get x sub 0, 0. The next one is 1/4. Oops, sorry, the next one meaning the first x sub 1, that's when I equals 2. Then x sub 2 is 1/2. And x sub 3 is 0.75. How can we write this? In general, what's x sub I minus 1? What's the pattern? Well, this number over here is just 1/4 times that. 1/4 times 0 is 0. 1/4 times 1 is 1/4. 1/4 times 2 is 1/2. So it's just 1/4 times whatever this is. In this case, that's I minus 1. So it would have been a little easier if we started from 0, went up to 3, and just had x sub I. But this works too. Okay? So this is what we have, where x sub I minus 1 is 1/4 times I minus 1. And now we can perfectly write this in function and sigma notation. And the advantage to this The advantage to this is it's much easier to go a step further, or another step further, and another step further. But before I get too ahead of myself, as a little definition, this is defined to be, that's what the colon means, by the way, like the definition. This is defined to be L sub 4, which is rectangle approximation, where the points on the left, that's why it's L, with 4 rectangles. We could go back and do R sub 4 by doing 4 rectangles on the right. See, when I say rectangle on the left, it's each rectangle, the height is determined by the point on the left. So if we wanted to do R, there's a lot I want to say right now. If we want to do R, we'd take the height from the right. And if we did this, this would be R sub 4. And we said L sub 4 was a little under. Do you think R sub 4 is going to be a little smaller as an approximation? No. R sub 4 is going to be bigger because look at this extra area. Look at this extra area. If we go from the right, in this case, we're going to have an over approximation of the area. All right. So we're going to take one step. And now maybe this step is not a step on a path. Maybe this step is kind of a step on a cliff, off of a cliff, or tumbling down a little bit. Just bear with me because there's a lot of cool, messy, confusing stuff in this section. Don't worry, this section is famous for confusing calc students everywhere. So just do your best. Let's take this guy and go a step further. Just one little step. One little step off a mountain. All right. This right here is L sub 4. So part 2 is, can you find L sub n? What if we have n different rectangles, an arbitrary number of rectangles? I think you can do it. Let's look. Let's get our picture back. We got this parabola, and we're, into some arbitrary number. We're starting at 0, we're going up to 1. We're doing an arbitrary number of rectangles. Who knows how many rectangles this is? Not me. Well, it's not that many. Let's say if there's n rectangles. Well, let's try to see what changes. So it's still going to be the sum. Do we start in the same spot, or are we going to start in a different spot? We're just adding more rectangles, but we're still starting in the same spot, so that part's the same. Well, if it was 4 rectangles and we had a 4 up there, what do you think is going to go up there if we have 5 rectangles? Well, it'd be 5. 6 rectangles would be 6. So n rectangles, we'll just put an n there. Where did this 1/4 come from? 1/4 was just the width of each interval. So if I have n of them, if I had 4 of them, each was a 1/4. 5 of them, each would be a 1/5. 6 would be a 1/6. There are n of them. Each rectangle width would just be 1/n. Okay. Still the same function. We're still going to write x sub I minus 1. But this time, x sub I minus 1 is going to be a little different. That's what it used to be. How does that change? Well, again, a 1/4 was just the width of each interval. The width is no longer a 1/4, it's just 1/n. And still going to be I minus 1. So we said there's going to be n rectangles. Let's see if we did it right. So the first rectangle, when I is equal to 1, plug in 1, you get x sub 0. It's 1 over n times 1 minus 1 is 0. Oh, the first rectangle is still at 0. That makes sense. The last rectangle is when we plug in n. You plug in n, you get n minus 1. 1 over n, I minus 1 is n minus 1. The last rectangle, all right, this one's a little hard to see. The last rectangle is n minus 1 over n, which simplifies to 1 minus 1 over n. That makes sense, right? That's going to be this point right here. The last rectangle isn't at an x location of 1 because we're looking at rectangles drawn from the left. So the first one is at 0, but the last one is going to be almost at 1. But we're one rectangle away. And each rectangle has length 1 over n. So we just found the approximation for the area using n rectangles with their height determined by the function on the left. And what's going to happen as n gets bigger and bigger? We're really starting to get into the next video now. I'm spoiling a little bit. I'll calm down. Okay. And as a side note, if you want this down in your notes, r sub n is going to be almost exactly the same. The only thing that changes between left and right is the index. It probably would have been easier to start with right and then go to left because the I minus 1 is a bit confusing. If you wanted this, the ones from the right is almost exactly the same. They're still the same width, but instead of doing the red dots, you draw them from the blue dots. So you just shifted over 1, really. Okay. Really maybe took a step off the cliff, but it's confusing, but it's cool when it all ties together. Let's do one more example and then be done with this video, okay? Example 4. We got more examples in the last video of the section, as always, the selected homeworks problem video. All right. Let's do right approximations. Use R4 to approximate the area under f of x equals x squared on the interval from 0 to 2, n equals 4. And you can do a lot of other things. You could find L4, you could find R6, you could do whatever you want. The best way to do this is always going to be with a picture. All right, so let's draw a picture. We know what a parabola looks like. Look like this. We're looking from 0 to 2. It goes on forever. So this is x squared. So the biggest x squared is going to get on this interval is at 2. And we want 4 rectangles. We're going to divide this into 4 equal pieces. So each one has to have a width of a half, right? And we're drawing rectangles on the right. So at the right of each interval, of each subinterval, that's where we draw the height of the rectangle. If it were the left, it'd look like that. Because it's the right, we always draw it up at the right, then down. Up at the right, and then down. Up at the right, and then down. All right? Oh, no, I'm not going to say it. I already said it accidentally. So what's the width of each of these? What's the height of each of these? Find that out and we're done. So the width of all of them is just 1/2. And the height is just whatever function value is at that point. This is going to be, the height will be 1/2 squared. The height will be 1 squared. The height will be 1.5 squared, because the height is the function value. So our area, our approximation, is just the width times the height of all of them. Well, they all have the same width, so we can just factor that out if we want. The height of the first one is 1/2 squared. Here, I'll use decimals to try to be consistent. Plus the second one squared, plus the third one squared, plus the fourth one squared, and you can just type this out. Quarter plus 1 is 1 1/4. 2.25 is 2.5. 6.5. I think you get 3.25. All right, and the actual amount I think is 8/3. That's like 2.6 repeating. We have a big overestimate here, which makes sense, right? There's all this extra area in our approximation. Okay, so that's the problem. That's the video. We got another long one. Next one's going to be better. Shorter, I mean. Maybe not better. This one was pretty fun, right? And then the applications one shouldn't be too bad either. So this is really the major squirrely one of the section. Let me know if you have any questions. Good luck. Have some fun with those left approximations, right approximations. Make sure to ask questions as you have them. And always draw pictures. They're going to make things easier. Bye-bye.